Today topic is zeros, singularities and residues. Zeros, singularities and residues. The first definition, zeros. Zeros of analytic function f of z. Zeros of analytic function f of z. What is the definition? Zero is nothing but a root. Zero means not zero. Zero means it's nothing but root. Okay. A zero of an analytic function. Zero of an analytic function f of z is the value of z for which f of z equal to 0. Nothing but what? This z value satisfying the function. Z value satisfying the function. That is called root. 0 is also called as a root of the function. Okay. Then, what is another one? For example, f of z equal to 1 minus e to the power of z whole square. 1 minus e to the power of z whole square. Then at what value it is 0? Clearly, f of z equal to 0 implies means what? 1 minus e power z equal to 0. E power z equal to 1. E power z equal to 1. So what are the roots? Yesterday I told you now. Z equal to 0 plus or minus even pi I plus or minus 4 pi I. Done? All these values. Nothing but z equal to 2n pi I, where n belongs to z, are the at all these values the f of z is 0, are the zeros or roots of f of z equal to roots of f of z. And in particular z equal to 2n pi I, n belongs to z, are the zeros of order 2. Zeros of order 2. Why? Because whole square is there. Why? Because whole square repeated. Okay. The roots are repeated 2 times. That is, it is zeros of order 2. Another example. If I take sin z, for example, f of z equal to sin z, then f of z equal to 0. When it will be 0, sin z 0 means what are the values of z? N pi. N belongs to z. Therefore, z equal to n pi, n belongs to z, are the zeros. Of order what? Not repeated. These roots are not repeated. Of order 1. This is about, I told already not to join after the class. Now, are the zeros of order 1. Next one is singularity. Singularity of analytic function. Singularity of an analytic function. Singularity of an analytic function. Already you know what is meant by singularity, where the function is not analytic at that point. Okay. That means definition, singularity. A point z equal to z naught at which the function f of z is not defined. A point z equal to z naught at which the function f of z, is not defined, means not continuous, not defined, or the function is not analytic, or the function is not analytic. We applied these two conditions in solving the problems, right? Already clearly one fraction rational function will be given, the function is not analytic at so and so point, so z equal to z naught, at which function is not exist, and our function is not analytic, is called singular point, is called singular point, is called singular point of f of z, singular point of f of z. Okay, for example, just idea, f of z equal to, yesterday we did this problem. Okay, f of z equal to 1 by e power z minus 1, 1 by e power z minus 1. F of z has singularities. The function is not defined at what point? Singularity is when e power z minus 1 equal to 0. So e power z equal to 1. So already I told you z equal to what values? 2n pi I, n belongs to z, are the singularities, are the singularities, are the singularities. Done? Okay. And one more point. You see, singularities are two types. Let me write. Singularities are two types. Two types. One is isolated singularity, isolated singularity, and second one is non-isolated singularity. Second one is non-isolated singularity. Non-isolated singularity. Non-isolated singularity. Okay. To get this non-isolated, the concept of isolated singularity, non-isolated singularity. First one, isolated singularity means isolated singularity. What is the meaning of this isolated singularity? A point z equal to z naught. A point z equal to z naught. Okay. Is called isolated singularity. First, it should be singularity, right? Singularity means the function is not analytic at that point. Okay. If we can find a small real number delta, isolated singularity, if we can find a small real number, delta greater than 0, positive real number, such that there is no other singularity. Isolated means what? Isolation means there is no other singularity, there is no other singular point, there is no other singular point of f of z in the neighborhood of z naught, in the neighborhood of z naught, neighborhood of z naught. What is the meaning of this? For example, this is z naught. At this point, the function is not defined, and in its a small neighborhood means this is small neighborhood. For example, if I consider this is small neighborhood with radius delta, then there should not be any other singularity here. In this small neighborhood, there should not be any other singularity. Means only one and only one singularity is there, that is z naught. In the neighborhood of z naught, there does not exist any other singularity of f of z. That is called isolated singularity. That is called isolated singularity. Example, same example, to explain the concept, I am taking same example. E to the power of z minus 1. E to the power of z minus 1. Singular points are what? Singular points are what? E power z minus 1 equal to 0. So e power z equal to 1. That implies z equal to what points? 2n pi I. N belongs to z. Now let me list the points. One is z equal to 0, right? Another one is what? 2 pi I. Another one is what? minus 2 pi I, next 4 pi I minus 4 pi I, and so on. These are the singularities. Are the singularities. Yesterday I told you now the concept. What is that? E to the power of z equal to 1 means what? E to the power of 2n pi I equal to 1. E to the power of 2n pi I means what? Cos 2n pi plus I sin 2n pi. What is this value? Cos 2n pi. Even pi, that is 1, and this is 0. So this value is 1. So this is the solution. These are the singularities. Now observe clearly where these points lies on the coordinate system. If I write x-axis, y-axis, just idea. This is z equal 0. Where is 2 pi I? Positive 2 pi I. That means on the y-axis. This is 2 pi. 2 pi means what? Okay, let me draw a very big one. What is this? X-axis, and this is y-axis. This is 0, 0.0. This is 0.0. Where is 2 pi? 2 pi means what? 2 into 3.6 point something. Okay, somewhere here 2 pi, somewhere here minus 2 pi. Got it? And what is the small vicinity of 0? That means small neighborhood of 0. This one. This is the singularity. This is the singularity. Similarly, where is 4 pi? 4 pi beyond 2 pi and beyond minus 2 pi. Right? That means in the small neighborhood of 2 pi, there is no other singularity. So this is isolated. So this is isolated. Same logic for remaining. This is 2 pi. For example, this is 2 pi if I take. Where is 4 pi? At a long distance. Where what is the small neighborhood of 2 pi? Only this one. You have to consider very small. So 4 pi is not belongs to this one. So all these are isolated. All the singularities z equals 0 are the singularities which are isolated singularities. Which are isolated singularities. Isolated singularities. Okay. Now coming to non-isolated singularity, let me consider another example. For this, I need that means in the vicinity of 0, I must get some other singularities. So let me consider tan 1 by z. Tan 1 by z. What is meant by tan 1 by z? Sine 1 by z by cosine 1 by z. Cosine 1 by z, right? Tan 1 by z. Then what are the singularities? What are the singularities? Therefore, singular points are, what are the singular points when cosine 1 by z equal to 0? Cosine 1 by z equal to 0. When cosine theta 0, odd pi by 2. Do you remember? Odd pi by 2. That means 2n plus 1 into pi by 2, n belongs to z. N belongs to z. That means what? What are the points? Z equal to what this becomes? Reverse. 2 by 2n plus 1 into pi. N belongs to z. So what the singularity is? Let me check. That is z equal to, when n equal to 0, if I take 2 by pi plus or minus 2 by pi, one can write. When n equal to 1, I will take, when equal to 1, 3 pi plus or minus 2 by 3 pi plus or minus 2 by 5 pi. See, observe this, all these points. And at infinity, at n tends to infinity, what is this becomes? 0. N tends to infinity, what is this value becomes? This is I am writing as n tends to infinity. Again, 0 is the last point. What is the before the last point? It is very, this next singular is, here before this 0, singularity is very nearer to 0. Observe this, very nearer to 0. Next, beyond this, that means what? If I consider, see, if I consider this is 0 as a singularity, I will write here limit n tends to infinity 2 by 2n plus 1 into pi. What is this value? 0. Okay, before infinity means it is also very large value of n. So in the small vicinity of this one, definitely there is some singularities are there, right? So I'm mentioning here, in this, since z equal to 0 is the singularity, and in the small neighborhood, in the NBD I will write small neighborhood of z equal to 0, there exist other singularities. There exist other singularities which are very nearer to 0, which are nearer to 0. Why I am mentioning this nearer to 0 means because of this. After this, before this 0, what is the next one? 0 0.0000 something, very nearer to 0. Hence, z equal to 0 is non-isolated singularity. Z equal to 0 is non-isolated singularity. Done? Okay. And others are what? Others are isolated. And others are non-isolated singularities. Others are isolated singularities. Now, in the syllabus, we have only isolated singularities. We have only isolated singularities. Got it? Okay. Now, next point is isolated singularity. Isolated singularities are classified in the following way. Okay. Now, listen. Whenever singularity is there, definitely, what is this singularity means? What I have Lorentz series expansion. So I will mentioning that if z equal to z naught is singular point, z equal to z naught is singular point of f of z, particularly isolated. I mentioned this, so now onwards I am not giving isolated always. If z equal to z naught is singular point of f of z, then f of z can be expanded in Lorentz series. F of z can be expanded in Lorentz series. What is the Lorentz series? That is, this is saying this concept is very important. If you do not understand this concept, we cannot go further. So listen carefully. If z equal to z naught is a singular point of f of z, then f of z can be expanded in Lorentz series. What is meant by Lorentz series? Positive powers plus negative powers. So let me mention a naught plus a1 into z minus z naught, a2 into z minus z naught whole square. These are all positive powers, plus what are the negative powers? A minus 1 into z minus z naught whole power minus 1, a minus 2 into z minus z naught whole power minus 2, and so on. And so on. Let's take this as equation 1. So one can write this as summation n equal to 0 to infinity an z minus z naught whole power n, and coming to negative powers, a minus n equal to 1 to infinity. See this change. This is minus n whole power minus n. Okay, this is Lorentz series expansion. Correct? Now, the first definition, what is the first classification is, first one is a removable singularity. First one is removable singularity. Now, what is meant by removable singularity? In the Lorentz series, of f of z, in the Lorentz series of f of z, if there is no negative power, negative power terms, that is what? Negative power terms means what? Quotients an minus n equal to 0. That is a minus n equal to 0 for n equal to 1 to infinity. Negative powers all become 0 when quotient a minus n equal to 0, n equal to 1 to infinity. Then Lorentz series of f of z about z equal to z naught. If there is no negative power terms, that is a minus n equal to 0, then z equal to z naught is called a removable singularity. See, in the word itself, it is there. Removable singularity. What is the meaning? Singularity is removed. That is removable singularity. See, what is this term? See, this term becomes what? Summation a minus n into 1 by z minus z naught whole power n. Correct? What is the singular point here? Z equal to z naught. I want to remove this singularity here. When this will be removed? If I make this a minus n equal to 0, then there is no singularity at all. This term completely absent. Only positive power series will be there. Positive power series means it is always exist. It is never possess a singularity. Never have a singularity. That is called a removable singularity. When z equals z naught is called removable singularity. If in the Lorentz series expansion of f of z about z equal to z naught, if doesn't contain any negative power terms, z naught is called removable singularity. Then one shortcut. What is that? Then or if, then I will write like this. Limit z tends to z naught. What is this f of z? See, if I apply limit for this function. If I apply limit for this function as z tends to z naught, what you will get? These negative terms are not there. These all negative terms are not there. Only positive terms are there. As z tends to z naught, what value you will get? Only constant value. That is, then limit z tends to z naught exist. Okay, I will write like this. That is, if limit z tends to z naught exist, then z equal to z naught is called, this is the criteria to decide whether removable or not. Z equal to z naught is called removable singularity. Removable singularity. Is that clear? Okay, this is over. Next one is what? Pole. Second one is pole. This is very, very important. Pole. And one more important point I forgot to tell. Let me write here. Negative power series is called, this negative power series is there now. This is called principal part. Negative power series is called principal part. Okay. This is called principal part. Remember this one, negative power series. So what is the definition of pole? If the principal part, in brackets I will write negative power series in Lorentz series. That is called principal part. If the principal part of the Lorentz series expansion, that means negative power series, okay? Lorentz series expansion of the function f of z, has only, this is important, has only finite number of terms, finite number of terms. Okay, that is what f of z equal to. Positive powers are there, a naught plus a1 into z minus a plus a2 into z minus a whole square and so on. Positive powers may be there, may not be there, doesn't matter. But When I coming to negative powers, all of you see a minus 1, z minus a whole power minus 1, a minus 2, z minus a whole power minus 2, plus and so on, having what term? See, Lorentz series expansion of f of z has only finite number of terms. Negative powers, principal part means I am considering up to m, z minus a whole to the power of m only, not infinite. This is full stop. This is full stop. Z minus Z naught, not A, all of you. This is Z minus Z naught. Z minus Z naught. Z naught. Got it? Okay, now I'm giving, that is, if the principal part contains principal part of Lorentz series, principal part of Lorentz series contains m terms, then this is important, only m terms, then z equal to z naught is called pole of order m. Pole of order m. This is important. Contains only m terms, up to m terms, then it is called pole of order m. Okay, this is the definition of pole. Then what is the criteria to find this? What is the criteria to find this? Therefore, a point z equal to z naught is a pole. If now condition is limit z tends to z naught f of z. What this becomes? If I take z tends to z naught, negative power is there. So 1 by z minus z naught. So definitely it goes to what? Infinity. Definitely it goes to infinity. And another condition is there. What is that? Since it is a pole of order m na, z tends to z naught, if I multiply this by f of z is multiplied by z minus z naught whole power m, z minus z naught whole power m, then this value exists. See, logic is what? This is multiplied by z minus z naught. What happened here? If I multiplied by z minus z naught whole power m, these are the positive powers only. Therefore, positive powers remains as it is. What is this becomes? Whole power m minus 1, m minus 2. And what is this becomes? 0. So, z minus z naught whole power 1 will be there. Plus m minus m, that is this value becomes 1. Only one coefficient will be there. What is that? A minus m. So what is limit then? Let me write for your clarification. If still any doubt, that is limit z tends to z naught, z minus z naught whole power m into, I will write like this, pole of order m. If what is this becomes? Limit z tends to z naught. What is the first term becomes? Done. Similarly, next term becomes what? Whole power m plus 1. I am writing all positive powers over. Coming to negative powers, a minus 1, z minus z naught whole power minus 1, and multiplied by this means m minus 1, m minus 2, z minus, m is positive real number, positive integer. M is positive integer. Remember this. Positive integer. This is m minus 2. And so on. What is the last term becomes? A minus m. This is bracket close. If I apply limit value, what is this? First term 0, second term 0, all are zeros. And what is the last one? Plus a minus m will be there. A minus m, finite value. That means limit value exists. This limit value exists. And when I take directly limit for f of z, definitely it goes to infinity. This is the criteria to find pole of order m. Got it? Okay. For example, still any doubt? See. For example, f of z equal to 4 by z minus 5 whole to the power of 5 plus 3 by z plus 2 whole to the power of some 3. Okay. Clearly, first identify singularities. Z equal to 5, z equal to minus 2 are the singularities. Are the singularities. Are the singularities. Then, what type of singularities? Classify the singularities. Question is, classify the singularities. Then what type of singularity these are? What type of singularity means? Is it removable singularity or is it pole? Like that I have to decide. Okay. Then what this becomes? What is the condition limit? Why it is not moving? Okay. Now let me take limit. First, coming to singularity z minus 5. If I multiply this by z minus 5 whole to the power of 5, as z tends to, what is the singularity 5? F of z. What this becomes? Check it. What this becomes? Check it. Yes. This one gets cancelled. Limit z tends to 5 will be there. And here only 1, 4 will be there. And here what? 3 by 3 into z minus 5 whole to the power of 5 by z plus 2 whole cube. I'm taking only one singularity first. So what is this value? 4 only exist, finite. Finite. Therefore, and what about the limit of finite? And one more I have to check. Limit f of z. If I take limit directly, z tends to 5. What is this? Becomes infinity. Therefore, z equal to 5 is pole. Pole of order 5. Pole of order 5. Similarly, z equal to minus 2 is pole of order 4. Pole of order 4. That's it. And to check whether it is removable or not, what I have to take? Removable singularity means this limit value must be finite. Limit f of z, z tends to z naught value must be finite. But this is infinite. Anyway, we will do more number of problems on this. And the last one is, third one is essential singularity. Essential singularity. So, isolated singularities are essential singularity. 3 types. First one is removable singularity. Second one is pole of order m. Third one is essential singularity. Essential singularity. What is that? See, if the principal part of the Lorentz series, principal part means negative power series part. If the principal part of the Lorentz series, of the function f of z has, what is this? Principal part has infinite number of terms, then z equal to z naught. Okay, Lorentz series of the function f of z about z equal to z naught. Okay, at then z equal to z naught is called essential singularity. Means what? That is f of z equal to, see, positive powers may be there or may not be there, doesn't matter. But for removable singularity, positive powers must be there. Okay, and so on. How many negative powers? Infinitely many negative powers. Pole means what? Only finite. This is clearly mentioned. See, what is this? Has infinite number of terms in principal part. Principal part means what? Negative power terms. That means this one contains infinite number of terms. Then that is called essential singular point. For example, see, Yesterday, I think we did one problem, 1 by, okay, let me take this one, e power 1 by z. F of z equal to e power 1 by z, right? So what is the singular point? Clearly, z equal to 0 is the singular point, right? Z equal to 0 is the singular point. And about the singularity, what is the expansion? So we have about z equal to 0, e power x expansion, right? 1 plus 1 by z, 1 by z square, e power expansion 2 factorial will be there, 1 by 3 factorial z cube, and so on. So all this which contains infinite number of negative power, infinite number of negative power terms. Therefore, z equal to 0 is essential singularity. Z equal to 0 is essential singularity. Yesterday we did one more problem. What is that? Another example. F of z equal to 1 by e power z minus 1, I think. Do you remember? Okay. Z equal to, actually, what are the singular points? We have considered 2n pi plus or minus n belongs to z. So z equal to 0. Let me take 0 first. Z equal to 0 is the singularity. Z equal to 0 is the singularity, right? Then what we did here in yesterday, let me expand this. Z plus z square plus z square by 2 factorial, z cube by 3 factorial, and so on, minus 1. So this one cancelled. Then I have taken z common. Do you remember? If I take z common, then what is this? 1 plus z by 2 factorial, z square by 3 factorial, and so on. Then I will consider this as one term. Okay. Then I have taken this one to numerator, 1 plus z by 2 factorial, z square by 3 factorial, and so on, whole to the power of minus 1. So this is taken as x, 1 plus x whole power minus 1 expansion, 1 minus x, z by 2 plus z square by 6, and so on. Just I am explaining briefly. Next term is what? This whole square, and so on. Okay, I am not writing. Let me take z inside. 1 by z minus 1 by 2, this is 2, minus z by 6, and so on. And so on. This is, what is f of z? Is the Lorentz series expansion. Is the Lorentz series of what given function? See, all of you, see this one. What is this f of series? F of z equal, let me write first positive power. Let me write first positive powers over. Infinitely positive powers are there. And how many negative powers are there? 1 by z only. That means 1 by 2, z by 6, and so on, plus z power minus 1. This f of z. Okay. That is, principal part contains only one term. Principal part itself, what? Negative power series term. Only one term. That means exactly this. Only one term. This one. Okay. Therefore, z equal to 0 is what? Pole of order 1 for f of z equal to, what is that function? E to the power of z minus 1. I think this clears the picture about the pole of order m. If it contains, for example, 2 terms, 3 terms, pole of order 2, pole of order 3, like that. Now, another definition. A pole of order 1 is called, it is named as simple pole. It is named as simple pole. A pole of order 1 is called simple pole. Okay, that means what? Z equal to Z naught is called simple pole. Simple pole as per definition, using the limit concept. If limit z tends to z naught, f of z tends to infinity. And what is another condition? Simple pole means what? Z tends to z naught, z minus z naught whole power m value 1 here. F of z exists. f of z exists. Okay, this is the topic about classification of singularities. About classification of singularities. Okay, uh, and there are some shortcut formulae are there to decide whether uh, that means residue. No, okay, no need of now residue. Now let me take some problems. Find the nature of the singularity of the following function. Find the nature of the singularities of the following functions. First one, f of z equal to z minus sin z by z square. Solution. Yes, first, function is not analytic at what point? F of z is denominator z square is there, not analytic, or function is not defined, not analytic at what point? Z equal to 0. When z equal to 0, what is this function form? 0 by 0 form. Means function is not defined. Function is not defined. Clear? Now, since we know the expansion of sin z about the singularity, we use that about the singularity z equal to 0. Okay, we proceed as how to proceed? F of z equal to z minus sin z by z square, that is equal to z. What is sin z expansion? Z minus z cube by 3 factorial, z 4 5 by 5 factorial, and so on, whole by z square. So one z gets cancelled. Let me take what is the common? Z cube will be common, isn't it, right? Okay, let me write z cube by 3 factorial minus z power 5 by 5 factorial, and so on, which is divided by what? Z square. So what is f of z becomes z by 3 factorial minus z cube by 5 factorial, and so on, which contains only positive powers, isn't it? See, only positive powers, which contain only positive powers. That is what? Negative power terms what? 0. That is, therefore, what is the singularity? Z equal to 0 is what type? Removable singularity. Is it clear? Right? Otherwise, another, what is the check? Just let me check. Limit z tends to 0 f of z. Limit z tends to 0. Z minus sin z by z square. Z minus sin z by z square. What I am getting? 0 by 0 form, right? 0 by 0 form we are getting. Therefore, what we have to do? L'Hospital rule, isn't it? 1 minus cosine z by 2z. Then what is this? Is again 0, again 0 by 0 form. So again L'Hospital rule, what I am getting? This is sin z by 2. Is it correct? Right. So 0 is what? Finite. Okay, 0 is finite. Therefore, since limit f of z tends to 0 equal to finite, z equal to 0 is removable singularity. This is another way of checking. See, I told this condition in defining the removable singularity. Is it correct? Where is that? Essential singularity. Yeah, this is pole. Okay. Yes, this one. limit z tends to z naught f of z exists, then z equals z naught is called removable singularity. Z equals z naught is called removable singularity. Now, another one, let me check. Next problem is, second problem is f of z equal to 1 by cosine z minus sine z. 1 by cosine z minus sine z. Anyone? First, f of z is not analytic or not defined function. Not analytic at what point? When cos z minus sine z equal to 0. Denominator is 0. So cos z equal to what? Sine z. Cos z equal to what? Sine z. Nothing but what I am getting, tan z equal to 1. When tan z equal to 1, that is z equal to pi by 4. Only one value, any other values? All of you? Tan 3 pi by 4, tan 3 pi by 4, tan 3 pi by 4, that is negative 1. 5 pi by 4, I think positive, correct? Are the singular points? Any doubts? Are the singular points? Then I have to check. Okay, there are two ways. One is what? First one, I will take pi by 4. If one is okay, that is better. What is this limit? Z tends to pi by 4. What is this? Sine z by, sorry, 1 by cos z minus sine z. What is this? Becomes infinity. It is infinity. Infinity means not, therefore, z equal to pi by 4 is not removable singularity. If it is finite, okay, not removable singularity. Okay, then now infinity is there, and another one is what? Another one is what? Limit z tends to pi by 4. Deciding pole. Deciding pole means, since the pi by 4 is not repeated, I will check like this. Pi by 4 is not repeated. So whole power 1 I am taking for to decide whether it is pole or not. To decide whether it is pole or not. For essential singularity, what is this? Must be infinity. Already we got infinity here, right? Let me check pole, whether it is satisfying or not. Z tends to pi by 4. Z minus pi by 4 by cos z minus sine z. What is this value? 0 by 0 form I am getting. Done. Now apply L'Hospital rule. Z tends to pi by 4. This value 1. This value minus sine z. And this value minus cosine z. So what is this? Sine pi by 4. It's not equal to 0, correct? 1 by minus 1 by root 2 minus 1 by root 2. So it is finite. It is finite, right? Since limit z tends to pi by 4, f of z tends to infinity, and the limit z minus pi by 4, f of z, this is whole power 1, remember, okay, is finite or exist, z equal to pi by 4 is pole of order 1, pole of order 1. Okay, that is simple pole. That is simple pole. Done. Now, another way. Let me just write. Say another way by using expansion. By using expansions, is it possible? But see, always remember what is the singular point here? Pi by 4, not 0. 0 is not the singularity. So don't expand sine z and cos z about z equal to 0. Our well-known expansions, not applicable. That is why I am not doing expansion. When z equal to 0 is the singularity, yes, I can express z sine z and cosine z in series expansion, the formulae. But the thing is not like this. Z equal to 0 is not the singularity, therefore no need to expand. This is the way. Okay. And already I told you essential singularity. Essential singularity I told you. Let me, that one also let me complete. F of z equal to e power 1 by z by z square. E power 1 by z by z square. Now, f of z is not analytic when z square equal to 0. That means z equal to 0. Z equal to 0. Done. Now what about z equal to 0 means? Therefore 1 by z I can expand. 1 by z I can expand, or you can apply the formula also, doesn't matter. This is, what is this? 1 plus 1 by z plus 1 by 2 factorial z square, 1 by 3 factorial z cube, and so on, whole by z square. So what is this? 1 by z square, 1 by z cube, plus 1 by 2 factorial z power 4, and so on. Okay, this is f of z, is the Lorentz series expansion, is the Lorentz series. About what singularity? Clearly z equal to 0, which contains infinite number of negative powers, infinite number of negative powers terms. Therefore z equal to 0 is an essential singularity. Essential singularity. Okay, this is about singularities and the classification of singularities. Classification of singularities. Any doubts?
Sir,